Alright, welcome back. We're working on 212. We're on the back side. We're going to look at the division property of square roots. See if we can use this property to help us uh, reduce radicals. If you take a look at the graphic up there, you see it says square root of a over b is equal to the square root of a over the square root of b. And basically, what that means is that take a look at number 1 on your paper. If I've got the square root of 4 over 25, in this case, I got a fraction in the radical. See, I can't have that. That's against the rules. But in this case, take a look. I've got perfect squares. The 4 is a perfect square, and the 25 is a perfect square. So what I do is they're both together, and I separate them. What I can get now is I've got a square root of 4 over the square root of 25. Now, I may not know what the square root of 4 over 25 is, but I know what the square root of 4 is, and I know what the square root of 25 is. So you do the square root of 4, get 2. Square root of 25 is going to be 5, and then you got 2 over 5 as being your answer. So then that's reduced. If you take a look at number 2, it's going to be very similar. It says square root of 16 over 36. All you do is separate them and take the square root of each one. Now, in number 3, it's a little different. Here, they already are separated. But the problem is they aren't perfect squares. In this case, it's actually to our advantage to go ahead and push them back together again. So what we're going to do is that we're going to create this fraction 21 over 7, because in this case I know what 21 divided by 7 is. 21 divided by 7 is 3. So when I've done that, now I can go ahead and simplify it and change that 21 over 7 to 3 and leave it under the radical sign. I can't have a radical or a fraction under a radical, but if it reduces down to a 3, I'm good. All right, so take a look at number 4, and you can see that that's pretty similar. Again, you can just put those together and divide. But number 5 is different. Number 5 is not much going on here. There's no perfect squares. I can't divide them, and I've got a radical in the denominator. Now, that's against the rules. I can't have that. It's kind of like the whole negative exponent thing. So what I need to do is figure out some way to get rid of that radical. Now, the easiest way to do that is to multiply both the numerator and the denominator by the radical that I'm trying to get rid of. If I multiply by square root of 7 over square root of 7, it's just like multiplying by 1, because whenever you multiply, square root of 7 divided by square root of 7, that's 1. So when I multiply it by that, I'm not really changing what it's worth, but I am going to change what it looks like. If you go across the top, 3 times the square root of 7 is going to be 3 times square root of 7. But square root of 7 times square root of 7 is going to be square root of 49. Now, what's nice about that is that I know what the square root of 49 is. It's going to be 7. And so now I've gotten that radical out of the bottom. And this is simplified. All right, if you take a look at the rest of them, they're all going to be one of those two cases. Number 6, we could go ahead and divide them. You know what 5 divided by 10 is. And then number 7, you're going to have to multiply both the top and the bottom by square root of 11. And in number 8, you can see it's got the square root of 6 over square root of 3. Well, you can divide that, so just put them together and divide it. Same thing with number 9. And in number 10, you're going to have to multiply the top and the bottom by square root of 2 in order to get that radical out of the bottom. Now, if you look in practice E, what's happening here is that we're going to be combining radicals. And it works a lot like combining like terms. Combine the coefficients of like radicals. Quite honestly, I'm not sure that the number in front of radical is supposed to be called a coefficient, but I do. So let's go for it. If you take a look at practice E number 1, I've got 6 square root of 7 plus 5 square root of 7 minus 3 square root of 7. Well, think of the 6 and the 5 and the 3 as being the coefficients. I'm allowed to add or subtract all those guys as long as the radicals, their multiplied times, are all the same. And in this case, they are. So 6 plus 5 is going to be 11. And then 11 minus 3 is going to be 8. And that leaves me with 8 square root of 7. Now, just like when you're combining like terms, the variable doesn't change. Well, in this case, the square root doesn't change. It stays the same. The only number that changes is the one out front. Take a look at number 2. In number 2, we do a couple different ones. We've got the 5 times the square root of 6, and then we've got a couple of the other ones that have square root of 7. So just like combining like terms, we're only going to put the ones together that have the same square root. So I'm going to take 5 square root of 6 and then the negative 1 square root of 6 and put those together. And I'm going to have 3 square root of 7 and 4 square root of 7 and put those together. So when I add the 5 minus 1, I get 4. And so that's going to be 4 square root of 6. And then when I take 3 plus 4, I get 7. And then I just leave it just like this. All right. Take a look at the rest of them. They all pretty much work like that. Just make sure that when you're doing these kind of problems that you only combine the ones that have the same square root like attached to it. And it's just like combining like terms. All right, now take a look at practice F. In F, what's happening is that we're going to take the square roots of these variables, and it works a lot like numbers. You can take the square root of a perfect square, but you can't take one that's not. The nice thing is that all even exponents are perfect squares. For example, what do you have to multiply times itself to get x squared? Well, you multiply x times x to get x squared. So the square root of x squared is x. What do you multiply times what to get y to the sixth? Well, you multiply y to the third times y to the third. So the square root of y to the third, the square root of y to the sixth is going to be y to the third. Now, in number 3, we get another extra letter in here. So we can do the first one, the square root of x squared, that's going to be x. We pull that out. Now, the thing is, we can't do the square root of y because it's not an even exponent. So we just leave that guy underneath. If you take a look at number 4, I've got x to the third power. Now, here, I've got an odd numbered exponent. But what I'm going to do is I'm going to rewrite it. So it's got x squared times x. X squared times x is the same thing as x to the third, but now I can see the perfect square. So now I take the square root of x squared, which is x, and that comes out from underneath the radical sign, and the x that I couldn't take the square root of, that stays underneath. The next one, if you see the number 5, I've got a 12. I've got to break that down to perfect squares. Well, 4 times 3 is equal to 12. And then the y to the third power I can break down to y squared times y. If you take a look at it, it's spread out, but they equal the same thing. 4 times 3 times y squared times y is equal to 12y to the third. But by spreading it out, now I can see all the perfect squares. So all I do is take the square root of those perfect squares. Square root of 4 is 2. I put that on the outside. I can't do anything with the square root of 3, so that stays inside. I got the square root of y squared, that's going to be y, that goes on the outside, and then the 3 and the y, they stay underneath. Now take a look at number 6, I've got x squared, y to the 4th, and z to the 5th. X squared, that's a perfect square, that's going to be x. Y to the 4th, that's a perfect square. The square root of that's going to be y squared, so both of those can come out. The one that is going to have to stay underneath is going to be z. Now, what I do with the z is I separate it and I change it from z to the 4th, or I'm sorry, z to the 5th, to z to the 4th times z. It's the same thing. It's going to be z to the 5th when you end up multiplying them. But now I just take all my square roots. Square root of x squared, x. Square root of y to the 4th, y to the 2nd. And then the z, it's going to be z to the 4th is going to be z squared. The only thing I couldn't do was the z, and that's going to stay underneath. So the last thing we've got to look at is the factoring things down at the bottom. Just keep in mind that when you're factoring, the first thing you look for is a GCF. In this case, there is one. We take out the 2, and we divide everything by 2, and we end up with x squared plus 5x plus 6. Now, there is no number in front of the squared term, so all I do is go straight to making the parentheses. I put an x in the front of each one, and then what I ask myself is, self, what times what equals 6? But when I add them together, I get 5. And I say, self, it's going to be 2 and 3. And 2 plus 3 is equal to 5, and 2 times 3 equals 6, and voila, we got that one done. If you take a look at number 2, it does also have a greatest common factor. In this case, it's going to be 3. When I divide everything by 3, I end up getting 2h squared plus 11h plus 12. Now, in this situation, I've got a 2 left in front of the h. So what I'm going to have to do is I'm going to have to use the x. So I put the 2 times 12 on top, that's 24. I put the 11 on the bottom. I look for two numbers that multiply to get 24 and equal 11. Well, that's 8 times 3. I bring down the 2 and put them underneath each one, and then I reduce it. And so now those are my factors. I've got the 3 comes down, and I end up with x plus 4, or I'm sorry, h plus 4, and then it's going to be 2h plus 3. All right, I hope you have a lot of fun with the rest of these, some of those difference two squares. Good luck with you. I'll talk to you tomorrow.